Hello friends, I welcome you all to this video. We are again with our fourth chapter titled as Power Spectrum Estimation, and here we are going to solve a simple problem based on to the spectrum estimation technique for the special case of the discrete time random process called as the moving average. In the previous video, we have understood the spectrum estimation for that particular type of the random process. So let us have the topic titled as problem moving average spectrum estimation. So we shall expect a simple problem statement, and by application of the estimate of the power spectrum for the moving average case, we expect the solution here. So let us begin with the topic. So here we can start with our topic problem moving average spectrum estimation. So very first of all, we start with the given problem statement. It starts with the estimated autocorrelation sequence of the random process x of n for the lags represented by k is equal to 0, 1, 2, 3 and 4 are represented are the rx of 0 is equal to 2, rx of 1 is equal to 1, rx of 2 is equal to 1, rx of 3 is equal to 0.5 and rx of 4 is equal to 0. Now we have been asked to estimate the power spectrum of the discrete time random process x of n for the following case known by x of n is a MA in bracket 2 process here. So, as we are already covered in this chapter, the various power spectral estimation techniques right from the periodogram, modified periodogram, Bartlett, Welch method, Blackman 2K method, minimum variance method, the maximum entropy method, and into the parametric approach, the autoregressive here. So, this problem is very similar with the same given details as we have solved for the previous case of the autoregressive spectral estimation technique there. So now in this case, the same given details we have to use for the power spectrum estimation when the input discrete time random process represented by x of n is MA in the bracket 2. So I can say that it is the second order moving average discrete time random process here. So in the previous video, as we have understood how to determine the estimate of the power spectral density for such a discrete time random process that has been generated by the use of filtering with respect to the noise W of n. So thereupon we have seen the two approaches, either to make the use of estimate of the auto correlation sequence or to make the use of estimation of the filter coefficients represented by q here. So b suffix q, thereupon we have represented the first approach, that it is the use of autocorrelation sequences. The estimates here will be the quite convenient, as in the given problem statement we have the autocorrelation sequence estimation readily available. These are rx of 0 is equal to 2, rx of 1 is equal to 1, rx of 2 is equal to 1, rx of 3 is equal to 0.5 and rx of 4 is equal to 0. So by making the use of the first approach that we have learned in the previous video, we can represent capital P cap suffix MA as a function of e to the power j omega. This is equal to, for the second order we have the summation k is equal to -2 to +2 operated over the estimate of the autocorrelation sequence Rx of k in multiplication to e to the power minus j times k into omega. Now in this summation we can make the substitution from the available estimation values of the coefficients here, and thus it results to the form 2 added to twice of cosine omega further added to twice of cosine of twice omega. So this becomes the required answer for the estimate of the power spectral density when the x of n is of the type MA in the bracket 2, the random process here. So this completes the solution to our problem moving average spectrum estimation. By the next lecture we shall continue into the same chapter to address one more spectrum estimation technique for another special type that is autoregressive moving average. Hence, the topic that it will be titled autoregressive moving average spectrum estimation. Thank you.